So the next layer we'll talk about, in the previous chapter we looked at the basics of physical layer. Now let's look at the data link layer, right? This is where things get very, very interesting. So as we have discussed earlier in the introduction chapter itself, what are the tasks, what are the key objectives of the data link layer? What does it do literally, right? It provides access to the medium, right? Here again, media basically means the medium through which you're going to transmit your signal, whether it is fiber optic cable, right? Whether it is fiber optic cable, whether it's wireless like Wi-Fi, or whether it's twisted cable, whatever it is, or coaxial cable, whatever it is, it provides us access to the medium on which we're going to transfer. That's the first task. The second task is called media access control, right? So what does media access control basically mean? We discussed this in the previous chapter also, but media access control basically means, imagine I have multiple hosts. All of them connected to the same medium. Let's assume all of them are connected like this. Okay, let's assume they're connected in a bus topology. Let's assume they're connected in a bus topology, and you want to transfer data from this node to this node. Okay, so let's call this node 1 to node 3. Let's say you want to transmit data from node 1 to node 3. So you want to transmit data from node 1 to node 3. At the same time, let's assume node 2 wants to transmit data to node 4 also. Now remember that since all these nodes are sharing a common bus, because it's in the bus topology that we discussed in the previous chapter, only one of them, either you can send data from 1 to 3 or 2 to 4 at a given point of time. You can't have both of them occur simultaneously, because the moment you have both of them occur simultaneously, what happens? Let's assume your node 1 or host 1 has sent some data to node 3 or host 3. Let's assume there is a frame that it's sending. While it is sending this through this, let's say, Ethernet cable, right? Which is a twisted cable, which is a type of twisted cable, right? And at the same time, let's assume 2 is also sending some data to 4. At the end of the day, these are electrical signals, and they will overlap and they'll corrupt each other, right? So at the end of the day, all of them are electronic signals. They are basically plus 5 volts or 0 volts. Now, if both of them happen to be there on the same copper wire simultaneously, they'll get jumbled up, right? So you cannot have both. You cannot have 1 transmit to 3 and 2 transmit data to 4 simultaneously. So media access control, look at the term here. It is going to control which node or which nodes or which pair of nodes have control over the media at any point of time. Again, bus topology is one of the simpler examples, but the same thing holds for other topologies also. So this is the second big task. The third biggest task is, if there is an error that happens when you're transmitting data from, let's say, node 1 to node 3, if there is an error that happens, or if there is a collision that happens, you have to be able to detect it and say, yes, there is some problem. I want you to resend the same frame of data. Okay, that's very, very important. Similarly, the data link layer also has some optional, again, these are not mandatory to be done by your data link layer, but most implementations of data link layer, like for example, in the TCP/IP protocol, right? It also ensures that there is flow control and acknowledgement. So what is it? First, let's see what is acknowledgement. Acknowledgement is a very simple concept. Let's assume I'm sending data from host 1 to host 3 or node 1 to node 3. Suppose I send the first packet. Then node 3 sends back. Suppose let's assume I send packet 1. Or let's assume I send frame 1. Again, oftentimes we tend to use these terms packet and frame interchangeably, right? But technically speaking, frame is what we have in a data link layer. Frame is the unit the unit of data in the data link layer, right? So frame is the unit. That's a more appropriate term to use. Suppose if I'm sending the first frame to, let's say, node 3, right? Then as soon as node 3 receives it, we want node 3 to send an acknowledgement. We want it to say, acknowledge that I have received 1. So that node 1 is sure that packet or that frame 1 has been successfully received by node 3 without any errors, and it doesn't have to resend it. Right? That's what acknowledgement basically means. We'll study more how acknowledgement actually works with different protocols. Right? The next concept is called flow control. Flow control, again, this is something that we have studied about, or we have briefly hinted about in the first chapter. Flow control basically means, imagine I have 2 hosts. Let's assume host 1 and host 3. Host 1 and host 3 may be able to receive data at different speeds because they're processing data at different speeds. So flow control basically ensures that if I have two hosts, let's say host 1 and host 3, which are transmitting data between each other, they can control at what rate. For example, I gave this example in the previous chapter also. For example, this is transmitting data at 10 Mbps, right? Or let's assume this can receive data at 10 Mbps, but node 1 is sending data at 100 Mbps. It's not able to process that. In such an instance, node 3 should be able to tell node 1 or host 3 to host 1. Again, I'll use the terms node and host interchangeably, right? So it has to send to node 1 or host 1 saying that, sorry, I can't process data at 100 Mbps. Please send it to me at only 10 Mbps. Only then I'll be able to process it. That's the job of flow control. Okay, these are the 4 things that we will study about through the rest of this chapter. And again, we'll study multiple protocols. We will study multiple protocols and multiple algorithms for, let's say, flow control. We'll learn multiple protocols for media access control. We'll study multiple algorithms and protocols for error detection, right? These are all very important aspects that we will learn about. Now, the data link layer itself oftentimes is broken up into 2 sublayers. There are broadly 2 sublayers. One is called the logical link sublayer. The other is called the media access control sublayer. Again, this is just a logical separation of your data link layer itself. So when people study data link layer, they break it down into 2 sublayers, and each sublayer has its own tasks. For example, the logical link layer is responsible for flow control. It is responsible for acknowledgement. It is responsible for notifying that an error occurred through the acknowledgement, right? The media access control is responsible for asking a very simple question. Who has access to the media at any point of time? Very, very simple question. The media access control is, as we saw just a while ago, media access control's job is to say which nodes have access to the media at any given point of time. And media access control, again, so I've talked to you about MAC address in chapter 1, right? So MAC address is an address. So MAC addresses are typically 12-digit alphanumeric addresses. 12-digit alphanumeric addresses, right? Again, these are not necessarily binary, they are alphanumeric. And every network interface card or Wi-Fi card that you have has a unique MAC address. Literally every computer has a unique MAC address of sorts, right? This MAC address uniquely identifies. Imagine I'm trying to transmit data from host 1 to host 2 to host 3. Let's assume all 3 of them are connected on in this type of architecture. Let's assume there is also host 4. Let's just say host 1, 2, 3, 4. Now let's assume host 1 wants to send data to host 3. Now let's assume host 1 wants to send data to host 3. How does it say that this data is meant for host 3 and not host 2 and host 4? It has to use the number host 3, right? So how does it uniquely identify host 3? It uniquely, because remember, this wire is connected to the network interface card. Remember, if you're talking about a guided medium, this wire, this physical Ethernet cable, let's take Ethernet as an example, right? This physical Ethernet cable is literally connected to the network interface card on each of these boxes or each of these computers or nodes, right? So each of them needs to have a unique address, a unique alphanumeric address. And that's what is called MAC address. Here MAC stands for media access control, right? MAC address is nothing but media access control. So the media access control sublayer is also responsible for providing unique addresses. It's responsible for unique addresses of each of the nodes. Now, suppose if I'm sending suppose let's take an example, right? Imagine I'm sending a frame. I say what is the source MAC address and the destination MAC address. So as soon as I place this frame on this Ethernet cable, this frame is now accessible by all. This frame passes through the physical wire. So it's accessible to all of them. But node 4 does not take it because it looks at the destination MAC address and it says, oh, this MAC address does not match my MAC address. So this is not meant for me. So I don't want to read it. Node 2 also reads, look at this. Node 2 is also connected. The physical wiring is connected. It looks at the destination address and says, oh, this is not meant for me. So let me not read it. Node 3 also reads the destination MAC address here and it says, oh, this MAC address is same as my MAC address, which means this is meant for me. So let me read it. Right? That's how things work internally at the wiring level. right? So MAC addresses are a very, very important piece. Actually, on Wireshark, let me show you this. On Wireshark, you can actually see the MAC addresses. For example, look at this, right? So this is my, okay, I'm just taking one packet here. Look at this packet. This is my IP address. This is the IP address of my computer. This is another destination IP address. I'm sending a UDP packet here. Again, in the previous chapter, I gave you a brief introduction to what UDP and TCP are, very briefly. Now, if you click on this, you get this packet. This is the whole packet information. Now, in the packet information, it says, okay, this is a frame, right? And it has 1152 bits in the frame. And if you just click here, it says, okay, look at this alphanumeric number, F0189897F259. So if you look at this 222222, 12-digit alphanumeric number. Okay, this is a 12-digit alphanumeric number. This is the MAC address of my Apple MacBook Pro, right? This is the source. Now, similarly, from where is this frame going to? It's going to my ASUS router that I have at my home. It's a wireless router. It's an ASUS router, and it's, look at this. It is the MAC address of my ASUS router here. Again, 12 digits. So this is the source. So I'm sending a frame from my laptop, which is an Apple laptop, and this is my MAC address, to an ASUS router whose MAC address is this, right? So you can go to any packet. If you take this packet, or you take this packet, okay, even in this packet, you can see the source and destination MAC addresses. This is not from my computer. This is from some other computer to some other computer. And look at what it says. It says this is the MAC address of the computer. This is the MAC address of the other computer, right? So very, very interesting thing that you can, again, that's why I recommend you please install Wireshark if you have not installed, because it will help you see what's happening on your computer right now. All the theoretical concepts we are learning, we can see it in reality, right? So again, this is what, again, logical link layer, media access control sublayers. These are two sublayers in the data link layer itself. Now, what all hardware devices do we have in the data link layer? You obviously have your network interface card. You have your Wi-Fi card. All these are communication devices that you have as part of your, like, this has a network interface card. You have your Ethernet cable. All of them are hardware which are part of your data link layer. Actually, if you think about it, the wiring itself is part of your physical layer, if you want to think about it. Similarly, there is a special type of hardware called as switches. And these are specifically called as layer 2 switches, because data link layer is layer 2, right? It's just above the physical layer. So this is nothing but layer 2. And these switches are often referred to as layer 2 switches. Like here is a diagram of a layer 2 switch from D-Link. Or from TP-Link, from TP-Link that I've taken from Wikipedia, right? So layer 2 switches, again, these are very, very useful. If you want to connect, let's say, suppose if I have a host here, suppose I have a host very, very far away. Let's say this is host 100, and I want to connect, these are very far away, right? To connect between both of them, sometimes I could use a switch. This will connect to this, right? This will connect to the switch, and this will also connect to the switch. I can place this switch somewhere in the middle path. So this switch, again, this is called as layer 2 switch, because there are something called as layer 3 switches also, which are nothing but routers. And in reality, as you have seen just a while ago, typically the most routers that you have in your home or office typically work as layer 2 switches also. In the earlier world, they had specific layer 2 switches. Today, your most modern routers also perform the same functionality that a layer 2 switch does. So layer 2 switch basically, look at what it does. Suppose this host 1 sends a frame. Right, with this destination. So it reads this and it routes this. Of course, if this signal has become too weak, it could also amplify that signal. Okay, if the electronic signal, the 5 volts, 0 volt signal became too weak, it could also work as a repeater, strengthening the signal itself. So switching, again, switches is again, we'll learn about routers and other things little later in the course. But there is a hardware device specific to data link layer called a layer 2 switch. We don't use layer 2 switches as often nowadays. We simply go ahead and use routers, which also perform the tasks of a layer 2 switch. Okay. So now there are 4 basic components in the rest of the course. We will first learn about flow control protocols. Okay, so we learned about flow control, right? The objective of flow control is to ensure that we are transmitting data between nodes at a speed that they can consume the data at, right? So we learn a bunch of flow control protocols. Again, most of computer networks is all about study of protocols. What is the advantage of each protocol, disadvantage of each protocol, what is the efficiency of each protocol, and things like that. Then we learn a bunch of multiple access protocols. This is all about this is all about media access control. This is all about media access control, right? So multiple access protocols basically help you understand which two hosts will have control over the medium, right? It's when multiple systems want to access, what protocols can we employ? There are a bunch of protocols that we'll study here. Then we'll also focus on error control, how to determine if there is an error and what to do if there is an error. Finally, we'll say how a frame is built. Remember, we get a packet from the layer above, right? We get a packet from the layer above, right? We get a packet from the layer above. How do I take a packet and convert it to a frame? What additional fields do I add to take a packet and to convert into a frame, right? That's what is called as framing. Again, these are the 4 important subtopics through the rest of this chapter that we'll cover in lots of detail. We'll study tons of protocols here, tons of protocols. We'll also measure the efficiencies of different protocols. We'll study why, what should be used and where things fail and everything like that, right? So before we go into the rest of the chapter, let me also introduce you to some simple terminology. Look at this. If I'm transmitting data from, let's say, host 1 to host 2, there are a bunch of physical delays that we will encounter. There are broadly 2 types of delays. The first one is called as transmission delay. The second one is called as propagation delay. Okay, let's just understand what they mean. Simple terminology, very simple mathematics. Okay, so transmission delay basically means, look at this, transmission delay basically means how much time does host 1 take to place the whole packet, okay, or the frame onto this line. How much time does it take to place? Suppose, imagine it has a packet or a frame. How much time does it take to place it on the wire? How much time does it take to place it on the physical wire which is taking this packet from host 1 to host 2? That's what transmission delay is, right? Then you have propagation delay. Propagation delay is all about once you have placed that packet once you have placed the whole packet onto your wire, how much time does it take for this packet to travel through this medium? Let's assume it's a copper wire. Like a twisted cable. Then how much time does it take to travel from here to here? That's what is called propagation delay, right? So we often use the terms T subscript T for transmission delay and TP for propagation delay. Now let's see how to measure it. Very simple. Suppose I have B, I use the term B, variable B, for bandwidth in bits per second, which means this is the bits per second. This is the number of bits I can actually place on the wire per second. So I can place B bits in 1 second. If I can place B bits in 1 second, I say my bandwidth is B. Bandwidth is measured in bits per second. Imagine if my packet or my frame, right? If my packet or frame that I have has L bits. Imagine it has L bits. Then how much time does it take to place L bits on this wire? So B bits in 1 second, which means 1 bit I'll take 1 by B seconds, right? And if I have L bits, how much time do I take? L by B seconds. Right? Very simple concept, very simple. This is like your high school mathematics, right? So the time for transmission is equal to L by B. So if you're given the size of the packet or the frame in bits and the bandwidth, which is nothing but how many bits you can place per second on the line, right? On this physical line, or if it's not a physical line, let's assume it's a wireless signal. How many bits you can place it on the wireless medium, right? If you have these two, your transmission delay is trivial to compute. It's literally trivial, right? Let's take some simple examples here. Again, so sometimes, again, there's a small caveat here. Sometimes when people measure data, when they say 1 kilo, they mean 2 power 10. Data is often measured in 2 power 10. But bandwidth, again, this is a convention that people follow, right? So when people say bandwidth, when they say 1 kilobits per second, when they're talking about bandwidth, what they typically mean is 1000 and not 1024. This is just a convention. Typically, whenever people say my bandwidth is, let's say, 1 kilobits per second, what they mean is not exactly 1024 bits per second. What they mean here is 1000 bits per second. But when people say I have 1 kilobit of data, what they mean here is 1024 bits. This is a simple convention. Again, there is a small difference. There is just a 24 extra here. This is a typical convention that many people follow, right? So again, in sometimes you're clearly given that they follow this convention. Sometimes you're not given that. So imagine somebody says that I have 1000 bits that I want to transfer. I have actually 1000 bits and my bandwidth is 1 kilobits per second. So 1 kilobits per second, because this is bandwidth, this is often measured in 1000 bits per second because it's a bandwidth. Data is always measured in 2 powers. Bandwidth is always measured in thousands, millions, billions, etc. So then what is this? Very simple. It's actually trivial. We have just seen how to do it, right? Again, this is just high school mathematics. So this is 1000 by 1000. So my transmission delay is 1 second. My transmission delay here is 1 second. Very simple. On the other hand, imagine if my data is 1 kilobits. What is 1 kilobit here? My packet size is 1 kilobit. 1 kilobit here means 1024 bits because we're talking about data here. Because we're talking about data. Bandwidth here is 1 kilobits per second, which means 1000 bits per second. Then what is my transmission delay? My transmission delay is 1024 by 1000, which is 1.024 seconds. So there is a small additional amount that you get here. Again, this is a typical convention followed by many people. Okay, even many books, articles follow this convention, right? Sometimes people do not follow this convention also. Let me also be clear about that. Sometimes people do not follow this. Sometimes people use a consistent terminology. People use 1K to mean 2 power 10 and 1K bandwidth also to mean 2 power 10, or they use 10 power 3. So the choice of using 2 power 10 versus 10 power 3, sometimes people use a consistent notation where for both data and bandwidth, they either use this or this. But I've also seen a lot of instances where people use, for data they use 2 power 10, for bandwidth they use 10 power 3. Just wanted to make that clear. Okay, so the next concept is called as propagation delay. This is very simple. Look at this. Once you place your, look at this, your total time to transfer a packet. The total time to transfer a packet is a combination of transmission delay and propagation delay. So how much time does it take to propagate a bit, right? 1 bit, how much time does it take to propagate from here to here? Very simple concept here. That's very simple. Look at this. If D is the length of the wire, if the length of this wire is D, and if a signal can travel at velocity V, which is meters per second, then the propagation delay, this is high school mathematics again, then the propagation delay is D by V seconds. Very simple concept. Again, remember, very often, if you use a copper wire, what is moving in the copper wire? Electricity, which is an electromagnetic signal. And if you notice, that's nothing, the electricity travels at the speed of light, right? Again, it depends on the medium in which it is traveling, right? It depends on the medium in which traveling. Light itself, so the velocity of light in vacuum, we often write it like this. Velocity of light in vacuum is 3 into 10 power 8 meters per second. The velocity of electricity, right? If there is an electrical thunderstorm that happens, if there is a thunder, right? Electricity also, because electricity and light, both of them are electromagnetic waves, right? They're literally electromagnetic waves, right? So in copper, electricity will flow at a different speed than in water. So in different mediums, for example, in Wi-Fi you have air and you're transmitting radio signals, which are also electromagnetic signals. The speed of the speed at which these signals travel is different in air, and it is different in vacuum. It is different in copper wires. It is different in your fiber optic cables, right? Which again use light exactly. So the speed or the velocity at which this is traveling differs from medium to medium. For example, let's take a simple example. So imagine I'm told that this wire is 2.1 kilometers. What is 2.1 kilometers? It is 2,100 meters, right? And I'm told that the velocity is 70% of the speed of light in vacuum, right? So the velocity of the medium, I don't know what this medium is, but I'm told that velocity in a given medium, that is connecting these two hosts, right, is 70% of the speed of light in vacuum. The speed of light in vacuum is 3 into 10 power 8. So 7 into 3 into, 0.7, right? 0.7. 70% is 0.7. 10 power 8 meters per second. This is the velocity. Now what is it? This is the distance. So what is my propagation delay? The distance, which is 2100 meters by the time it takes. So this is 0.7 into 3 is 2.1. 2.1 into 10 power 8 seconds. Right? Very simple concept. Now what is 2.1 into this? So 2.1 into 1000 is this. So 2.1 into 1000 is this. Right? 1000 by this is 10 power minus 5 seconds. Right? This is 10 power minus 5 seconds. And we know that what is 1 microsecond? 1 microsecond is 10 power minus 6 seconds. Right? 1 millisecond is 10 power minus 3 seconds. We have studied these in this in computer organization. Right? 1 nanosecond is 10 power minus 9 nanoseconds. Right? So what do I have? I have 10 power minus 5 seconds. Right? So which means, obviously I can represent this in terms of milliseconds or microseconds or nanoseconds, obviously. Right? So 10 power minus 5 is 10 into 10 power minus 6 seconds. Right? That's what 10 power minus 5 is, which means 10 microseconds. This is nothing but 10 microseconds. That's all it is. So the time it takes, or the propagation delay, not the transmission delay, propagation delay here is 10 microseconds. Very simple concepts, right? The reason I introduced these two concepts of delays, the transmission delay and the propagation delay, is because we will measure the efficiencies of many of these protocols using these two metrics, using transmission delay and propagation delay.